Greetings, class. It's good to be with you. This lecture component is going to be on probability theory. It's for Whitlock and Schluter Chapter 5. This will also be useful for Jessica Utz Chapter 16. Now, as we begin, I would like to start off with some scripture. Colossians 1:16-17 says, "For by Christ all things were created, in the heavens and on earth, visible and invisible. All things have been created through him and for him. He is before all things, and in him all things hold together." He grounds the very rules or laws of the universe which allow probability to occur in the way it does. In addition, Proverbs 16:33, "The lot is cast into the lap, but its every decision is from Yahweh." So somehow he's even in control of the probabilistic events. That's something for us to ponder. Now, getting into it, let's go for it here. Background, this began in the 1600s, modern probability theory conceptions, in a letter exchange between French gentlemen, Pierre de Fermat and Blaise Pascal. Pascal, by the way, was an ardent Christian. He wrote the famous Pensées. He had the famous Night of Fire, after which he wrote his encounter with God down on paper and sewed it into his jacket so that he would never forget. Very powerful. Now then, they gave us the modern foundations here, and so I want to get into the basics. And I know you've done some reading, so we'll try to simplify this and get into the questions. First rule, sum of the complements. We're going to use the following notation. If I say P, and then in parentheses, some event, usually uppercase letters at the beginning of the alphabet, that's the probability of event A occurring. Sometimes we can have conditions. So, for example, if event A depends upon event B, then I will denote that by probability of A given B, which, for shorthand purpose in this lecture, I'm just going to use an upper bar. So the probability of A given B is denoted here. And then lastly, if you have an event A, let's say that this is the space of all possible events here, and A is in this circle, then outside of that circle is A complement. That's all events that are not A. That should get us the notation we need. Now, the probability of A plus the probability of A's complement is said to be 1, and that can be shown from this diagram right here. The probability of all events inside the box is going to be 1, and so A complement. Hopefully clear. Now, let's do the AND rule for probability. I have two different events, events A and B. We denote by the AND or this intersect symbol for my math majors. And the way we do that probabilistically is the product, probability of A times the probability of B. However, if the two events are not independent, there's some dependency relationship, then that is probability of A times probability of B given A. At this point, I'm going to leave that as it is, and I'm going to draw a diagram for it in a little bit. I want to move into the third rule. I've inserted an extra space here for some notes in a bit. So, third rule is the OR rule. Okay? If A and B are mutually exclusive, that is, they're non-overlapping, then here's event A, here's event B. Their probability is simply the sum of the two probabilities. There's nothing to worry about there. On the other hand, if they are not mutually exclusive, that is, there's an event in common to both A and B, at least one, could be more than one. this circle is events A, this circle is events B, then I'd like to point out that this inner part is those events both A and B, okay? And we need to worry about them, because if I add the two circles together, I'm double counting this inner region. So to get the right result, we simply have to add the two and subtract off the intersection. Okay, now still looking for a diagram for the AND case. Let us cover independence. Events A and B are independent conceptually if one doesn't affect the other. So if I take a single fair six-sided die, let's suppose, we give this baby a roll, and ta-da, we roll it. Maybe we get a 6. Okay, when we roll that guy, then, or let's suppose we get a 1. Then we could ask ourselves, okay, let's roll it again. What's the probability that we get a 1 again? Well, as you know, that's 1/6 of getting a 1, and it's 1/6 of getting a 1 even though the previous roll was a 1, because subsequent rolls on the die are independent of one another. Now, this gives us the mechanism by which we can test for independence. So we define two events, A and B, as being independent if the probability of event A is the same as the probability of event given B. If that's the case, then A and B are said to be independent. Show us a counterexample. To do that, we're going to look at cards, which I define the deck a little bit later. But the standard deck consists of 52 cards, okay, 4 suits. This is the suit called clubs. This is the suit called diamonds. This is the suit called hearts. And lastly, the suit called spades. As you can see in each of the 4 suits, they all have the same 13 cards, namely ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then there's a jack, a queen, and a king. Okay, so if we're going for it here, what's the probability that we get a jack? All right, well, I've got 4 suits, and so to randomly select from the deck here, there's 1 jack in the hearts, and I've got 4 such cases, so there are 4 out of 52 jacks. And then what's the probability of a jack given the previous card was a king? Well, now again, if I'm only just kind of browsing around here, let's suppose I pulled out the king of hearts. Well, now that the king of hearts is missing from the deck, how many cards are there? There's only 51 cards left, okay? And how many jacks are there? Well, there's still 4. But those two are not equal, and so subsequent draws from the deck, as long as we don't put them back, that's called without replacement, are dependent. Now, let's go on for a diagram then. So to get my dependence diagram here, I'm going to come, and I'm first going to consider the independent case. I'm going to make sure to get this right the first time. Okay, let's go back to dice to start us off here. And I'm going to draw, okay, we're going to have 2 possibilities on the dice. We're going to have that the dice turn out to be odd or even, and this will be our first roll. So the probability of getting odd, as you all know, is 1 out of 2. That'd be the 1, 3, 5. Probability of even is a 1 out of 2, and that would be the 2, 4, 6. Now, let's consider the second roll, and on that second roll, we will again do the odd and the even cases. And now, because we've already established that subsequent rolls are independent, then we know that the probabilities don't change. So I've got 1/2. and then I've got 1/2 for even. What that gives then is this square right here is going to be the probability of odd on the first roll and odd on the second roll, which is the probability of odd on the first times probability of odd on the second, and there's no worrying about conditioning. That's going to be 1/2 times 1/2, which is 1/4. Using the same exact reasoning, 1/2 times 1/2 is 1/4, 1/2 times 1/2 is 1/4, 1/2 times 1/2 is 1/4, and you'll note that the sum of all of these entries is 1 for 100%. We have the complete independence case. Now, let's move into the dependent case. It's going to be very similar, and you'll keep the independent handy. Dependent case. All right, we're going to use the same exact start here, except there's going to be one twist. We're not going to use a die now. I'm going to conceive that we have 6 slips of paper, 1, 2, 3, 4, 5, 6, in a hat. Okay. When I start on that first draw, there's still a 1/2 probability of occurring, and we can catch this by just a 1, 2, 3, 4, 5, 6. Okay, construe these as cards, let's say. I shuffle the cards. What's the probability of getting an odd? Oh, 5. Okay, well, there's a 1 in 2 chance of that occurring. So we got that. Even, same. 1/2, even. And that is our second. Excuse me, that's our first draw. Now, second draw, things change. I'm going to have odd again, and I'm going to have even. But if I pulled an odd, we had a 5 coming out, right? So 5's out. What's left? 1, 2, 3, 4, 6. What's the probability of getting an odd on 1, 2, 3, 4, 6? I only have 2 odds left now. So given an odd on the first, we now move into a 2/5 probability of odd, 3/5 probability of even, and we see a change. However, if even came out first, then probabilities of odd on the second draw change. Probabilities of odd now, let's just stick the 5 back in, and let's suppose that we pulled this 2 out, pulled an even out. What do we have left? We've got 2, 3, 4, 1, 3, 4, 5, 6. And so with the 1, 3, 4, 5, 6, that gives us 1, 3, 5. I've got 3/5 odd and 2/5 even. Now, let's consider this event right here. This is the probability of even on the first draw, odd on the second draw, and that's probability of even on the first times probability of odd on the second given the even. Given even on first. Oh. Okay, that was a little trip out. Sorry about that. Okay, so even on the first was 1/2. Odd on the second, this is the second draw, given even first, so even first, that was 3/5. So 1/2 times 3/5, which is 3/10. So this one has 3/10 probability. down here we can see is 2/10. You could simplify to 1/5. It's easier to hold it in tenths for the moment. This one is 3/10. Now we can observe that the sum of the inner probabilities here is still 100%, but we've got a picture of and. It's the product of the row and the column, and we have a picture of independence, which is when the columns do not have the same proportions. And again, you could say that for the rows, but it's easier to view it from the columns. So that covers our different probability rules. Now, for a couple of examples, and then we close. How are we doing on time?